What if the next cure for Alzheimer's isn't discovered in a petri dish, but inside a paradox? What if the solution to climate change isn't just about building more solar panels, but about unlocking a new state of matter designed by an intelligence that operates on the fundamental laws of the universe? It sounds like the stuff of a blockbuster sci-fi movie, but this isn't fiction. This is the new reality dawning at the intersection of two of the most powerful forces humanity has ever conceived: artificial intelligence and quantum computing. Today, we're not just looking at a new technology. We're peering into the dawn of a new computational era. We're talking about quantum machine learning, or QML, a fusion so profound it promises to solve problems that are not just hard, but were previously considered impossible. This is the moment where the logical, pattern-seeking mind of AI meets the strange, probabilistic, and almost magical world of the quantum realm. We'll explore how this convergence could invent new drugs, forge revolutionary materials, and reshape our entire global economy. But we'll also confront the monumental challenges and the profound ethical questions it raises. What happens when our most powerful tools become too complex for us to understand? Buckle up, because your conception of what a computer can do is about to take a quantum leap. Let's dive in. Before we can run, we have to learn to walk. And before we can understand QML, we have to rewire our brains to think about computing in a radically new way. For your entire life, you've been surrounded by classical computers. Your smartphone, your laptop, the servers running your favorite streaming service, they all think in a language of absolute certainty. That language is built on bits. Picture a light switch. It can be on, or it can be off. A 1 or a 0. It's binary, straightforward, and incredibly reliable. This is the bedrock of our digital world. Trillions of these switches, flipping billions of times per second, create everything from a simple email to a complex video game. But they have a fundamental limitation. A switch can only be in one state at a time. It's either on or it's off. There is no in between. Now, let's step into the quantum realm. Quantum computers don't use bits. They use qubits. A qubit isn't a simple light switch. Imagine instead a spinning coin. While it's spinning, is it heads or tails? The answer is, in a sense, both. It exists in a cloud of probability, a state of pure potential. This is called superposition. A qubit can be a 0, a 1, or an infinite spectrum of possibilities in between, all at the same time. It's only when we force a measurement, when we stop the coin and look, that it collapses into a definite state of either heads or tails, a 0 or 1. This ability to hold multiple values at once is the first source of quantum computing's power. But it gets even stranger. Let's talk about entanglement, a phenomenon Albert Einstein famously called spooky action at a distance. Imagine you have two of these quantum coins, and you entangle them. This creates a deep, unbreakable connection between them. Now, you give one coin to a friend who travels to Mars. You stay here on Earth. The moment you stop your coin and it lands on heads, you know with absolute certainty and faster than the speed of light that your friend's coin on Mars has just landed on tails. Their fates are intertwined, no matter the distance. This isn't communication. It's a shared existence. So, why does this bizarre, almost mystical behavior matter for machine learning? Because it allows for a new kind of parallelism. Let's use the maze analogy from the article and really paint the picture. A classical computer solving a complex maze is like a single explorer with a flashlight. It tries one path, hits a dead end, backtracks, and tries another. It methodically checks every single possibility, one by one. If the maze has a billion paths, this could take an eternity. A quantum computer, thanks to superposition and entanglement, is like flooding the entire maze with light at once. It explores every possible path simultaneously. It doesn't find the exit by trial and error. It senses the shape of the solution from the interplay of all possibilities. This isn't just about being faster in terms of clock speed. It's about a fundamentally more efficient way of navigating vast, complex problem spaces. This is the quantum advantage, the key that could unlock problems currently far beyond the reach of even the world's most powerful supercomputers. So we have this phenomenally powerful new way of computing. What happens when we merge it with machine learning? At its heart, classical machine learning is a master of finding patterns in high-dimensional data. But high-dimensional in the classical world is one thing. In the quantum world, it's another universe entirely. This is where that mind-bending quote from Dr. Maria Schul comes in. A 300-qubit system can represent more states than there are atoms in the universe. Let's pause and truly absorb that. It's not just a bigger number. It's an exponentially larger canvas on which to work. If a classical computer is painting on a sheet of paper, a quantum computer has a workspace that is, for all practical purposes, infinite. This allows QML to see relationships and solve problems in ways that are simply unimaginable for classical AI. Let's break down how. One of the most promising near-term approaches is quantum kernel methods. This is a hybrid model where the quantum computer acts like a special coprocessor for a classical AI. Let's make this tangible. Imagine you're a data scientist trying to predict which customers are likely to churn. You have a messy dataset of customer behaviors. A classical algorithm tries to draw a line or a plane to separate the loyal customers from the at-risk customers on a flat graph. It can be incredibly difficult if the data points are all mixed together. A quantum kernel method takes this messy, flat data and projects it into that enormous quantum feature space we just talked about. It's like taking a tangled mess of red and blue threads, lying on a table and magically lifting them into a three-dimensional space. Suddenly, from this new vantage point, all the red threads are clustered on one side and all the blue threads on the other. Separating them becomes trivial. You can just slide a piece of paper between them. That's what a quantum kernel does. It finds a new dimension or perspective where complex patterns become simple. In medical imaging, this could mean finding the subtle, almost invisible signature of a tumor in an MRI scan that a classical system would miss. Then we have the more futuristic concept of quantum neural networks, QNNS. These are not just classical neural networks running on faster hardware. They are entirely new architectures built from quantum circuits, using principles like superposition and entanglement as their core building blocks. Their true power may lie in analyzing data that is itself quantum in nature. Think about chemistry and materials science. The way molecules interact is governed by the probabilistic rules of quantum mechanics. A classical computer can only ever approximate these interactions. A QNN could, in theory, simulate them perfectly because it speaks the same native language. It would be like trying to understand Shakespeare by reading a bad translation versus reading it in its original English. This could unlock the design of new medicines, hyper-efficient solar cells, or catalysts that pull carbon out of the atmosphere. For you, the business owner, this could mean forecasting models that don't just predict next quarter's sales, but simulate the entire market ecosystem to identify opportunities no one else sees. For you, the student, it could mean a learning platform that understands not just what you know, but the way you think, crafting a truly personalized educational path in real time. The potential is breathtaking, but we're not living in that future just yet. So, where are we on this journey? We are firmly in what scientists call the noisy intermediate scale quantum, NISQ era. Let's break that down. Intermediate scale means we have machines with a few dozen to a few hundred qubits, not the millions we'll eventually need. Noisy is the real kicker. Imagine trying to perform a delicate symphony in the middle of a construction site. That's a NISQ computer. The qubits are incredibly fragile. The slightest vibration, a stray magnetic field, or even a tiny temperature fluctuation can cause them to lose their precious quantum state. This is called decoherence. The noise creates errors in the calculations. These early machines are the quantum equivalent of the first vacuum tube computers of the 1940s. Massive, temperamental, error-prone, but a critical first step. So how do we do anything useful with such flawed hardware? The answer is teamwork. The most promising QML algorithms today are hybrid variational algorithms. This is a brilliant partnership between the old and the new. The classical computer acts as the steady, reliable project manager. It does the bulk of the work, preparing the data, defining the problem, and optimizing the parameters. The quantum computer acts as a highly specialized, incredibly powerful consultant. The classical computer says, "Hey, I have this impossibly complex function I need to evaluate. I'll send you the parameters." The NISQ device, for a brief fleeting moment before decoherence sets in, uses its quantum magic to calculate the result of that one specific hard part of the problem. It then sends the answer back to the classical computer. The classical computer looks at the result and says, "Okay, that's interesting. Let's tweak the parameters a bit and try again." This loop repeats, with each component playing to its strengths until they zero in on a solution. We're already seeing this in action. The quantum approximate optimization algorithm, QOA, is a perfect example. Think of a global logistics company like UPS or DHL. They face a monstrous optimization problem every single day, millions of packages, thousands of vehicles, and a constantly changing landscape of traffic, weather, and delivery windows. Finding the absolute best route is a classic combinatorial explosion problem. QOA is being tested to find better than classical solutions, potentially saving millions in fuel and drastically reducing delivery times. Similarly, the variational quantum eigensolver, VQE, is the workhorse of early quantum chemistry. Its goal is to find the ground state energy of a molecule, its most stable configuration. This is the absolute key to understanding how a drug will interact with a protein in the body. Companies like Menton AI are using VQE to simulate molecules for drug discovery, a process that could one day shrink the timeline for developing life-saving medicines from over a decade to just a few years. These are not science fiction. They are the first tentative steps into a larger world, taking on the noisy, brilliant machines of today. While the promise is real, the path forward is steep and fraught with challenges that are as immense as the potential rewards. Building a fault-tolerant, large-scale quantum computer is one of the greatest engineering challenges in human history. First and foremost is the hardware and error problem. The noise we talked about isn't just an annoyance. It's a fundamental barrier. The solution is quantum error correction. But here's the catch. It's incredibly resource-intensive. The backup singer's analogy from the article is perfect. To create one stable, reliable logical qubit, you might need to chain together 1,000 or even 10,000 noisy physical qubits that are constantly checking and correcting each other. So, to build a truly useful quantum computer with 1,000,000 logical qubits, we might need a machine with 1,000,000,000 physical qubits. The engineering and material science required to build, network, and cool such a device is staggering. Next is the data loading bottleneck. This is a subtle but deadly problem. QML algorithms are great at processing quantum data, but most of the world's data, your financial records, medical scans, satellite imagery, is classical. To use a quantum computer, you have to upload this classical data and encode it into a quantum state. This process can be so slow and inefficient that it completely erases any speedup you would have gotten from the quantum computation itself. It's like owning a Ferrari, but having to fuel it with an eyedropper. Researchers are working on concepts like quantum random access memory, QRAMM, which could theoretically solve this, but it's still highly theoretical. Without a solution, QML will be limited to problems where the data is either small or naturally quantum to begin with. Finally, there's the interpretability or black box problem. We already grapple with this in classical AI. A deep learning model might be incredibly accurate at identifying cancerous cells, but we often can't ask it why it made a particular decision. Its reasoning is buried in millions of mathematical weights. QML takes this problem to a whole new level. Because of the observer effect, the fact that measuring a quantum system collapses its state, we can't easily peek inside the computation while it's happening. It's like trying to understand how a cake is baked, but the oven door is locked and opening it instantly vaporizes the cake. As Dr. Nathan Weed so aptly put it, we're inventing new ways of computing that don't always align with our classical intuitions. How do you trust a financial model that could make or break your company if its internal logic is fundamentally unknowable? How does a doctor trust a QML diagnosis if the machine can't explain its reasoning? This isn't just a technical hurdle. It's a philosophical and ethical one. Overcoming these mountains will require decades of relentless innovation, collaboration, and a few history-making breakthroughs. Despite these challenges, the seeds of the quantum revolution are already being planted in fertile ground. Let's look at where QML is moving from theory to reality and what it could mean for your life. Drug discovery and personalized medicine. This is arguably the most exciting near-term application. Companies like Rocco and Menton AI pioneering this space. Imagine a future where, instead of the current blockbuster drug model that works for a percentage of the population, medicine is truly personal. A QML simulation could model how a specific drug molecule interacts with your unique proteins based on your own genetic code. This could lead to hyper-targeted cancer therapies with fewer side effects, or drugs that halt neurodegenerative diseases like Parkinson's in their tracks. It's a shift from reactive to predictive, from one-size-fits-all to bespoke medicine. Material science and sustainability. Think about the limitations of our current technology. They often boil down to materials. We need better batteries for electric vehicles, more efficient solar panels, and stronger, lighter alloys for aerospace. Researchers at Google Quantum AI are using all to simulate the quantum behavior of electrons and materials, allowing them to design novel materials from the ground up. Picture a world with room temperature superconductors that enable a lossless global energy grid, dramatically cutting our carbon footprint. Or batteries that charge in seconds and last for weeks. This is how QML could help build a more sustainable and technologically advanced civilization. Finance and economics. The global financial system is a chaotic, complex, adaptive system. Firms like JPMorgan Chase are exploring QML for tasks that are currently intractable for classical computers, like optimizing massive investment portfolios with thousands of assets or running hyper-realistic risk simulations that model black swan events. For an investor, this could mean more stable and resilient retirement funds. For the global economy, it could mean better tools to predict and mitigate financial crises before they happen. Climate science. Our climate models are incredibly complex, but they are still crude approximations of reality. QML could process vastly larger and more complex datasets from ocean sensors, atmospheric readings, and ice core samples to create climate models with unprecedented fidelity. This would mean more accurate predictions of sea level rise, more reliable forecasts for extreme weather events, and better tools for policymakers to make informed decisions to protect our planet. For a farmer, it could be the difference between a successful harvest and a devastating loss. These aren't distant dreams. These are active research areas where QML is already demonstrating a potential advantage. The quantum future isn't a single event. It's an unfolding process, and we are living through its very beginning. So, what does the road ahead look like? In the next 5 years, we'll see QML solidify its niche in highly specialized domains like quantum chemistry and materials discovery. Within a decade, as hardware improves and error correction becomes more viable, we might see the emergence of more general-purpose QML applications that begin to outperform classical methods on a wider range of optimization and machine learning problems. Beyond that, the horizon is truly breathtaking. Imagine a world where a QML-powered AI is a true scientific partner. It wouldn't just analyze data we feed it. It would design its own experiments, identify patterns no human brain could ever conceive, and formulate novel hypotheses, dramatically accelerating the pace of discovery itself. In your daily life, the impact will be ambient but profound. It won't be a quantum button on your phone. It will be the impossibly efficient logistics network that delivers your goods, the perfectly tailored medicine that keeps you healthy, and the clean energy that powers your home. Even creative fields could be transformed, with quantum algorithms generating art or music based on principles of superposition and entanglement, creating aesthetics we can't even imagine today. But this incredible power demands equally incredible responsibility. This brings us to the ethical dimension. Dr. Al-Haim Kashi's warning is critical. We must build ethics into QML from the start, not as an afterthought. If we are not careful, these powerful, opaque systems could inherit and amplify the biases present in our data, creating a new generation of black box discrimination that is almost impossible to challenge or even detect. As policymakers and citizens, we must demand transparency, advocate for robust testing, and create frameworks for governance that ensure these technologies serve all of humanity. This also creates an urgent need for education. We are on the cusp of a massive talent shortage for people who are fluent in both quantum physics and machine learning. If you are a student today, this intersection represents one of the most exciting and impactful career paths of the 21st century. For educators, it is a call to create new, interdisciplinary curricula that can prepare the next generation of quantum natives. As we draw this deep dive to a close, what can we take away from the story of QML? For me, the first lesson is the sheer power of human curiosity. QML exists because for over a century, brilliant minds refused to accept that the universe should make sense according to our limited classical intuition. They kept pushing at the edges of reality, and now we are learning to harness that strangeness to build a new world. It's a profound reminder that our greatest innovations come from embracing the unknown. The second lesson is the power of convergence. QML isn't just a better AI or a better quantum computer. It is a new entity, born from the fusion of two fields. It teaches us that the future won't be built in silos, but in the collaborative, often messy, spaces where different disciplines collide. And finally, this story is a call to action for all of us to remain adaptable and intellectually agile. The pace of change is accelerating, and the paradigms we take for granted today may be obsolete tomorrow. The ones who thrive will be those who stay curious. So here's my advice for you. You don't need a PhD in physics to be a part of this journey. Stay curious. Read articles, watch videos, follow labs like IBM Quantum and Google AI on social media. If you are in a field like finance, logistics, or medicine, start asking the what-if questions. What is the most complex, seemingly impossible problem your industry faces? Because that is likely where QML will strike first. And most importantly, participate in the conversation about ethical development. Demand that the tools we build reflect the best of our values. Now, I want to turn it over to you. What excites or perhaps even scares you the most about quantum machine learning? Can you think of an impossible problem in your own life or work that you would hand over to a quantum computer? Share your thoughts in the comments below. Let's build a community of curious minds exploring this frontier together. If you enjoyed this exploration into the quantum realm, please show your support by liking this video, subscribing to our channel, and hitting that notification bell so you don't miss our next dive into the technology shaping our world. Until next time, keep exploring the frontiers.